University of Denmark, or in Danish, Danmarks Tekniske Universitet. And its aim is to develop and create value through technical and natural sciences for the benefit of the society. And it was founded by Hans Christian Ørsted, the founder of electromagnetism in 18th century. So it's been 200 years since the discovery of electromagnetism, and that was done by H2S Ørsted, and he was the founder of DTU. And so DTU was founded in 1829, and then it went through several transitions and mergers and so on, up until what is now known as the Technical University of Denmark. So one of the mottos of DTU is technology for people. So our research is to support our education, innovation, and to provide scientific advice to the public and private sector. As you can see, DTU is located. DTU is located here in Northern Europe, in Scandinavia, in Denmark, and basically its main campus is in the northern part of the city of Copenhagen, called Lyngby, and it has several other campuses around the country, as well as some research facilities in Greenland. So where do I come from this tiny country called Denmark, Northern Europe, and then northern part of Copenhagen, and DTU is located in Lyngby, and this is the Little Mermaid, which is very symbolic for Denmark, and everybody is very proud of her here. It's a piece of nice artwork. And this is the Nyhavn, one of the pictures places in Copenhagen, and this is DTU's central administration building. So with that said, I'm going to start my talk on hydrogen sulfide scavenging and process intensification. And first and foremost, I want to thank my collaborators and PhD students for making significant contributions to preparing this lecture. So what we're going to cover today is talking about where's the motivation and challenge for process intensification, then looking back inside process synthesis and intensification, and bottom-up approaches for process intensifications, and later on what are the objectives of taking on such an approach. And then we're going to talk about the framework, and then we're going to show some application, an application example on the hydrogen sulfide, scavenging and valorization, and we're going to draw some perspectives and conclusions towards the end. So there are basically several challenges that our society is currently facing when it comes to converting resources to products, the usage of energy, water, and the waste that we're generating, and all the different types of environmental impact. So there are different challenges that need improvements. For example, the economics is always a centerpiece of all improvements, and the idea is that we use improved and sustainable technologies and processes to reduce the capital and operating expenses and maximizing the profitability, while at the same time we want to generate less waste and be more efficient in use of our raw materials, and we want to have a more sustainable and environmental friendly production of products, and having such sustainable process systems. So at the moment, roughly around 25% of resources are converted to valuable products that fulfill a need in society. This should perhaps improve significantly up to 40% in the future. And the grand question here is that how are we going to achieve these improvements? And one way to actually answer this question and achieving these improvements is to be more innovative and to have more sustainable designs based on reducing the waste, recovering resources, circular economy concepts, and in general more sustainable process development. So process intensification is basically to synthesize innovative and intensified processes by integrating process synthesis and process intensification. I have provided references to some of the background work of this presentation, so you can refer to them. So I'm not going to go into the details of some of these concepts that I'm tackling here. So basically, the search space of unit operations is extended by generating new and innovative solutions through process intensification. And process intensification is basically that you want to arrive into a more sustainable process alternative that by integrating phenomena, tasks, or unit operations to have multifunctional or integrated processes. For example, here we have a reaction and we have a separation. This is how the processes basically are. This is process, and then if we integrate the reaction task with the separation task, we could arrive into a unit operation, an intensified unit operation, like a reactive distillation. Right. So, and then what we are actually doing here is that each one of these tasks could be broken down into a set of phenomena, so that by combining the phenomena, the fundamental phenomena, right, then we can basically build the processes bottom up. So if we break down, let's say, a process and its functionalities and the phenomena that are involved in it to carry out the task, whether it be separation or reaction, then we can actually do this phenomena-based process intensification. So the key attributes to generate intensified solutions are how systematically we can determine innovative and sustainable solutions. Is there a way that we can, by setting some targets, we can systematically identify the innovative and sustainable solutions in the fastest and most efficient way? And how can we basically compare these solutions with each other and screen them? How the complexity of them when they're supposed to be brought into an industrial landscape are supposed to be managed, and how do we guarantee optimality or non-trade-off solution when we are, for example, considering environmental, technical, and economic constraints. So in a nutshell, process intensification is considered as transition from pure unit operation thinking to more integrative approach. So there are different methods for process intensification. So basically, the methods that are developed for process intensification to address these questions are should be systematic, should be flexible and versatile. I mean, they are multidisciplinary. They need to be able to tackle different types of processes and systems. They're quick and efficient. we want to quickly and efficiently generate innovative alternatives, and at the end, we want to manage the complexity, screen them, and find the optimal solution for our desired objective. So here is an overview of the process intensification approaches. The process intensification is being carried out in different categories, such as heuristic-based methods, mathematical programming methods, or hybrid methods at the different levels of aggregation at the process level, unit operation level, or at different scales, at the phenomenon scale or task scale or unit operation scale, and different application domains. So the bottom-up approaches for process intensification, they depart from the conventional unit operations approach, the highest level of aggregation. So in the conventional unit operation approach, we typically start with knowing what is the unit operation, what is its functionalities, and then we try to do the improvements on the given unit. Whereas there are several processing tasks, physical-chemical phenomena, and functions that are used to generate unit operations, and in that way, we will have different process alternatives. So there are a number of methodologies based on bottom-up approach. So in bottom-up approach, you want to first start from the physical and chemical properties of the systems and understand the fundamental functionalities of a unit operation. And then by combining those functions or phenomena in a logical way, we want to rebuild either the same unit operation or arrive into an innovative solution in a bottom-up approach. There have been a number of attempts over the past years. You can have the reference. You can look at the references here. This is actually this work refers to the PhD work of Nipun Garg, a former PhD student at DTU, who advanced these methodologies. And here I will, in this presentation, I'm going through his methodology actually, and there's a little bit of error down there. I will, in the version that I sent you, Everton, I'm gonna fix this so everything is readable. So these methods span across heuristic, mathematical, and hybrid methodologies. The phenomena-based approaches use physical and chemical and functional insights into the unit operations, and then a building block approach that mimics the fundamental phenomena are actually assembling the blocks of different phenomena in a logical way to arrive into unit operations that can carry out the task, right? Separation, reaction, heating, cooling, phase transfer, phase contact, and so on. So in a way, once they are logically connected, either we arrive into existing set of unit operations, or we can be innovative and possibly find innovative solutions by combining the phenomena bottom up. So here the methodology that is going to be presented in this work is a multi-level and multi-scale framework that can simultaneously and systematically perform process synthesis intensification, either for an existing process or for a completely new problem, that by considering the complete search space. And as I said, the idea here is that in principle, by combining the phenomena in a logical order, one should be able to rebuild and arrive into both existing and novel intensified unit operations. So the framework is systematic, and it's it's not just that it can generate the existing processes, but it can also generate some innovative solutions which may be worthwhile considering for further development. So new phenomenon, their classes compared to previous works in the series are embedded in this framework. The flow sheet is generated at three levels. The phenomena-based superstructure, there are rules for physical property and thermodynamic insights and ranking of generated alternatives. And finally, there are potentials to generate novel solutions based on a ranking approach, which is on energy resources, considering at the lower level of aggregation. So basically, what is phenomena-based synthesis? So it was basically proposed first time by Lutze and co-workers in 2012. They introduced the concept of phenomena building blocks. They developed a unity operation and phenomena-based process intensification method, and they applied it to different case studies. Later on, it was expanded by Babi and co-workers in 2015. They developed the three-stage approach on synthesis design and innovation, as you can see. So first, they were finding actually the optimum sequence for the processing route to produce a product from raw materials. And then once they find that optimum solution, they arrived into an optimal design that then later on by analyzing that process design and identifying its bottlenecks, then they were targeting the bottlenecks through the phenomena-based process intensification to arrive into more innovative or sustainable solutions, thereby improving the overall sustainability of the process, including the process intensification towards the end. So they include economic life cycle and sustainability analysis to identify the process hotspots of their design. They intensified hybrid solutions for vapor liquid systems are proposed, and they also applied their methodology to three different case studies. And they have shown that they could actually generate non-trade-off solutions. So in phenomena-based synthesis, most of the processes can be represented by different combinations of 8 key phenomena, referred to as phenomena building blocks. So these are the phenomena building blocks, such as mixing, reaction, two-phase mixing, phase transfer, energy supply, phase contact, phase separation, and dividing. So using the different, by combining the different phenomena building blocks, I mean, different unit operations can be generated. So these phenomena are the ones that are affecting the different driving forces in different tasks in the process, and they are desirable phenomena. For example, these are different building blocks, and then if we look at the reactions, then reactions can, in principle, take place at in different phases and conditions, and so on. So this is how then each phenomena building block then is associated to additional constraints. So why the phenomena-based approach? The reason for it is that it operates at a lower level of aggregation compared to other levels, such as the task level or unit operation level. it does not constrain the analysis by the existing unit operations. So it will facilitate the maximum degree of freedom and the largest search space to generate innovative solutions. And different phenomena can be interconnected to form novel unit operations. So the phenomena-based synthesis, in principle, removes the bias from the existing unit operations. Instead, it facilitates identifying both existing unit operations as well as innovative unit operations. So basically, the concept of the phenomena-based process synthesis is very similar to the computer-aided molecular design, where in computer-aided molecular design, first we start with atoms, for example, carbon, hydrogen, and oxygen, whereas in phenomena-based synthesis, we have, for example, the phenomena building blocks, mixing reaction, or other phenomena, and then by combining atoms, we are going to generate groups, and basically by combining the phenomena, we are gonna generate the SPBs, and then by combining groups, we can get the molecules, and by combining SPBs, we can actually generate the unit operations. So, and then we in computer-aided molecular design, we screen the feasible candidates to see if they exist or they do not, if that molecule exists, or if it does not exist, and then we rank them based on the target properties that were desired for the target molecule that had to be designed, and also. So same goes for the phenomena-based synthesis, where we screen feasible flowsheet alternatives. So the unit operations, as you can see here, they can be translated into tasks. For example, here is a reaction. It is translated into a reaction task, and then basically phenomena building blocks are combined. For example, we have the mixing liquid with the reaction in the liquid phase. This is one phenomena building block, and then again we have the mixing, the liquid mixing, and another phenomena here that are combined to describe the tasks. So they're together. Let's say if it is cooling, for example. Then together they're generating one SPB. So this SPB represents this task. Or for separation, it is similar. For example, in a distillation, we have mixing, we have cooling, we have two-phase mixing, we have phase contact between vapor and liquid. We have phase transfer between vapor and liquid, and we have phase separation between vapor and liquid in the top of the column, and then we have the middle part of the column, and then towards the bottom of the column we have heating, for example, which is different from the cooling. So by combining these three phenomena building blocks, then we can now arrive. Once we combine the SPBs, then we can generate a new feasible solution. So we had the separation SPBs, and then we had the reactions. We had the reaction SPB, and then we combined them. And then, as you can see now, the reaction term is actually showing up because the rest were actually similar. We had this here, but combining this, so the only thing, and then we had the liquid mixing. So the only thing that is gonna go in is actually the reaction. So now we are gonna have this set of SPBs, and then so this is a combination of reaction and separation task, and this is giving us a reactive distillation. So this is how the framework works, and And same set of phenomena can be also so translated to different unit operations as well. So as you can see, so this is basically the combined SPB for a reactive distillation column. Or, for example, also there's the possibility to go from this combination back into the unit operation. So if we have this, then we can actually hypothesize something else. So if it's a reaction and separation task, then basically we could think of a divided wall reactive distillation. For example, as you can see, so now we could by decomposing these two tasks into their phenomena building blocks and combining them with the logical rules, we could actually design new intensified alternatives that could carry out the same task if they were just sequential, if they were just separate from each other. So basically, this is the framework. The framework that Nipun has developed has 4 stages, 13 steps, and 12 algorithms, and 4 knowledge bases. So the first stage is the synthesis analysis, when we analyze the given system. We need to define the problem. What are the inputs? The inputs are typically raw material, reaction, products, production targets, and so on. And then we need to also define what are the performance criteria as the output, what are the process inlet outlet information. Then we need to analyze the process. We need to analyze both the reaction and mixture. We need to have the information, pure component properties of the components present in the process. And then we need to basically identify the azeotropes, miscibility gaps, eutectic points, and also construct the binary matrices. And here we have the base case analysis. So we have 2 options here. If a base case is available, meaning that we have an existing process that we want to look for an intensified alternative to it, and if this base case is available, basically we generate the task and phenomena-based flow sheet, just like the example that I showed. And then again, there are some input-output information that we need to identify, and then we need to identify additional tasks and phenomena, identifying the process hotspots, and finally design targets and additional list of tasks and phenomena. But if once then we have that, then if a flow sheet is not available, then we can actually generate different flow sheet alternatives, which that also means additional steps need to be carried out, like generation of mathematical combinatorial superstructure of compounds. We identify the phenomena building blocks. We generate the list of feasible SPBs. We generate the phenomena-based superstructure. We reduce the alternatives available in that superstructures, and then we combine the basic structures to generate flowsheet alternatives, and then finally we translate the basic. I'm not going to go into the details of this, but the references to the prior art are available, which if you're interested, you can go through them and learn more about the details of this. So this pretty much to show you an overview of how this framework works. But now once we have a flow sheet, then we or flow sheets, basically we rank all alternatives, and then we need to verify the analysis, and then we need to basically rank and compare the alternatives to see which one is finally matching our desired targets set in our problem formulation. So now that was an introduction to the phenomenon-based process synthesis intensification for natural gas processing. So now here's an example on offshore natural gas processing intensification. So assuming that natural gas is composed of methane, CO2, and H2S. Methane goes for power generation, CO2 to be better capture it or avoid releasing to the environment, but it is separated. And then the idea is that basically the hydrogen sulfide, we have two options. Either we have to neutralize it, or better than neutralizing, if we can, we see if we can generate value out of it. Currently, what happens to hydrogen sulfide through different processes is it's a catalytic reduction to elemental sulfur, or in some cases, production of sulfuric acid from it, or in some cases, but just using a chemical to convert it to a less corrosive, less hazardous compound, and then transport it somewhere else or dump it somewhere. So mitigating hydrogen sulfide in various application domains is often an expense. But here we want also, through intensification, we want to see could we turn around the economics around it, and then perhaps turn it into a revenue stream. So what we are doing is that, so we follow the application, the methodology. So basically we have three different compounds in our stream. We have obtained their thermodynamic properties, and basically we applied the phenomena-based process synthesis, given the properties and so on. We identified the possible phenomena that could carry phenomena building blocks. We combined the phenomena building blocks and two SPBs, and now we want to see what could be the potential innovative process alternatives that could be used in this context. So first we did a pure component analysis of the mixture, and then basically we developed the binary ratio matrix. So where's binary ratio matrix? So binary ratio matrix is based on a process synthesis methodology based on thermodynamic insights. So here the point is that every unit operation actually is based the separation characteristic of every unit operation is basically based on one or some of the pure component properties of the compounds that are supposed to be separated in that system. For example, if you think of distillation, then the characteristic pure component property for separation in distillation column is a boiling point. So if you want to separate compound A from compound B in a distillation column, the larger the difference between the boiling points is, the easier that separation would be. And the closer that number is to 1, that means that the distillation becomes a less feasible solution, right? So basically, process synthesis based on thermodynamic insight means that if you break down your process, its components into their set of pure component properties, you obtain the pure component properties, and then, for example, like this CH4 and H2S, for example, A and B, you calculate the ratio between their molecular weight, then this molecular weight boiling point. So, for example, 1.9 is the difference between their boiling point. That means that the distillation could be an option, right? So melting point, maybe crystallization could be an option, and so forth and so forth. For example, we have the radius of gyration, which is 17. So that means that maybe membrane could be also an option. So in this way, we are identifying a set of feasible unit operations or tasks that can do the job. Using those, then we break those then down to the phenomena building blocks, and then we start our endeavor from there and applying the phenomena-based process synthesis methodology. So here's translation of the feasible alternatives at the first level. So we have now, out of these three components and their binary ratio matrix and the potential different operations that could be done, we have broken down the separation, and then we have come up basically with the sequential absorption, which involves a mass separating agent. Now we have translated these feasible alternatives, and as you can see, we are finding actually, for example, here we are finding a multi-adsorption column, right? Or here we are finding a column that has a membrane and it has an adsorption. Or here we are finding a divided wall adsorption column. So you see, I mean, the framework is generating innovative solutions. I mean, some of these solutions may well not exist, or nobody may have looked at them. But the fact that the methodology can generate such alternatives provides a lot of insight on how the development could be done, and it provides a lot of good ideas for future development. And several other intensified alternatives are also identified here. For example, here is where you send the mixture, you add the two mass separating agents, and here is a breathable film that could be in the middle of the column to do the separation between the B and C. So as you can see, a lot of different alternatives. I mean, in this case, more than 100 different alternatives have been generated, but I'm not showing all of them, but these are just examples that how different alternatives could be obtained. Finally, there's verification and ranking of the alternatives. Of course, for some of the absolutely innovative alternatives that there's no proof for them, I mean, you can continue study them or you can leave them because their TRL level is just so low. You could try to do a literature search or use a knowledge base to see if there are some indications of their development and find information. And then basically you can carry out process modeling or simulation to actually find detailed information about your final alternatives and then try to rank them. So one of the alternatives coming out of this methodology was a liquid-liquid phase transfer catalytic system for valorizing H2S. So again, when we're talking about the process intensification, it happens at the different levels of aggregation, phenomena, tasks, and unit operations. So if you look at the phenomena level, we had the reaction, two-phase mixing, phase contact, and phase transfer. And then the hypothesis for using this phase transfer catalytic system is now we obtained that from the phenomena-based process synthesis framework, but we didn't have the information. Now what we want to do here is a multiscale modeling of the system to actually understand how does that particular unit operation when it comes to H2S works. There are indications of phase transfer catalytic systems in the literature, but no application for H2S has so far been reported. That is where we want to now investigate. So we want to, the idea with valorizing H2S is that instead of looking at H2S as a hazard, we could look at it as a sulfur-rich compound and see how we can actually use that to produce valuable compounds that could instead generate revenue streams. And then we have looked at the application in the offshore oil and gas production. And if the process gets too large, one option could be to place it actually on a ship, and then it can go to the platform, drag it, convert it, and do whatever different things. But there are key challenges in identifying key reactions and accessing to details of the techno-economics and so on. So our hypothesis here is a phase transfer catalytic system, which came out of the phenomena-based process synthesis intensification framework. So this is how does the H2S system of concern offshore is working in the Danish part of the North Sea in the oil and gas production. To mitigate the H2S, they use a chemical called triazine. So triazine is a chemical that reacts with H2S and forms a solid component. It causes a lot of problems sometimes in the produced water, because if it is unreacted, then it goes to the produced water and then it is dumped offward. It can create hazards to the aquatic life. On the other hand, it can cause fouling in the transportation pipelines from the sea to the shore to the refinery, and there are different challenges around it. So now our hypothesis here is that we use a phase transfer catalytic system where there's a H2S rich aqueous solution, and there's an organic solvent and organic reactant. So we have an organic phase and we have an aqueous phase. So this organic phase and aqueous phase are basically in touch with each other. So we have this in the organic phase, we are going to up concentrate the sulfur containing products, and in the aqueous phase, we are going to have dissolved H2S. And the way that the phase transfer catalyst works is that it dissipates in the solution, so it drags a reactant from the organic phase to the aqueous phase, and vice versa. And so basically it transports the ions between the two phases and lets the reaction happen in either phase. And once the reaction happens, it is again released from that molecule and goes back and continues like this until the reaction is complete. So here's where we want to actually put a phase transfer catalyst system, or a biphasic reactor with phase transfer catalyst on an offshore platform. Again, this is the process intensification concept. So the phenomena identify the reaction, two-phase mixing, phase contact, and phase transfer. And we have them all here. And this is the scheme of the phase transfer catalytic system, and the advantage with the phase transfer catalysis solution is that it offers a solution to the fact that not all substrates are soluble in the same solvent. So, and in such case, a reaction is not simply possible, but given the feature of a phase transfer catalyst, you can actually do this transport of ions between the phases, and basically making that reaction possible. But to do this, we needed to have properties. There are different property prediction methods, such as group contribution methods or Cosmo-based methods. For group contribution methods, we need prior experimental data. The experimental data on sulfonated compounds in the literature is quite scarce. So methods such as UNIFAC were not as accurate, but when we go to Cosmo models and then they modeling the sigma profiles of a molecule and then using the density functional theory, even if we do not have the experimental data from the quantum chemical information, and we can actually obtain properties of a given molecule. So that is where our multiscale modeling scheme comes into the picture. So we have the cosmotherm, and then we have the turbomole where we do the molecular and electronic simulation of the system, and then we go and then we in an optimization environment, basically we solve the process level equations. So cosmotherm deals with the statistical thermodynamics, whereas turbomole then basically, given that information, we basically obtain the sigma profiles of a molecule, and given that information, then we can predict the properties. And that is basically the approach we're taking. So the computational algorithm is such that once you have a molecule, in this case, we didn't have the properties for the PTC, we didn't have the properties for the H2S and the AQ solution, and so on and so forth. So what do we need to do? We need to model all these molecules. But the good thing with that is that once you have modeled one molecule, you don't need to do that twice. So you can store that in the database, right? So once you actually do the density functional theory calculations and the structural and energetic calculations, then you can store them in database, and then you can basically use them in your process model. So in the case of valorizing H2S, as I said, you're gonna basically replace or add this unit operation to the existing process. These are some details of the reactions that happen in the organic phase and the aqueous phase. And the model results show that there's a good agreement between some experimental data that we had obtained from the literature and our predictions from the model. And if you look at now the economics, basically here, the idea is to produce benzyl mercaptan from H2S using benzyl chloride as a raw material, and toluene as a phase transfer catalyst. So if you look at the economics of this, I mean, there's a very lucrative economy around actually this solution, and basically, if we assume that the current activities is at something like $40 million expenses, if you just convert using such a reactor H2S to some green products that have no economic value, you still actually improve this NPV, but by another 18 million. And then if we actually go to our benzyl mercaptan solution, I mean, the NPV could completely turn into a positive landscape of $77 million. And this is a sensitivity analysis on the concentration of H2S. It has a huge impact on the economics of this process. So, I mean, the process, I mean, and the reaction needs to be such that the price of your product should be such that with the amount of H2S that you have, it is economic. So depending on the choice of product that you choose, because in a phase transfer catalytic system, by changing the reactant and the phase transfer catalyst, if you can identify the right one, basically you can change the product. So the life cycle assessment of the new solution had to be carried out. Here, we identified a set of 9 green solvents and alternative reactions using the green solvents and the economics around them on how we could look into alternative solutions than benzene mercaptan. Here is the sustainability of these different PTC that we have identified. And so finally, the challenges and obstacles are the new products creating new revenue streams with little market depreciation and less environmental impact. The validation and feasibility of identified reaction pathways and process schemes based on the model-based approaches needs to be investigated. Control monitoring is crucial because intensified processes pose a challenge when it comes to control and monitoring because of the loss in the degree of freedom as a result of integration of function or unit operation. So control of them is rather important. So that was it, and thank you very much. So I think I kept the time. And
thank you so much, Professor, for this awesome presentation. And 5 years ago, Professor Fernando and I, we were working for Petrobras. SEMPS Petrobras is the research center of Petrobras down here in Brazil. And we were working in an interesting project using, because that time, I don't know today, nowadays, but that time,